Hi, welcome to this next video in linear programming duality. In this video, we're going to be discussing the concept of weak duality in linear programming. So weak duality is actually a concept that we've already seen show up in these videos on linear programming, but we haven't actually formally named the concept yet. So in this video, we're going to formally name and hence distinguish this concept, and we will also discuss the logical consequences of this feature of linear programs. So for what we do in this video, for the most part, we will be considering a primal-dual pair of linear programs, where the primal is a maximization problem that you can see here on the left in a general form, and the dual is the corresponding dual linear program that you can see on the right. So the statement that we will make about weak duality will be made assuming that the primal is a maximization problem and the dual is minimization, but there's an entirely analogous statement that you can make if instead the primal was minimization and the dual was maximization, because as we've seen before, the dual of the dual is the primal, so it doesn't really matter which one you call primal and which one you call dual. You just need to know that they come in a pair and one is the dual of the other. But in order to make a concrete statement, we are going to just take the convention that the primal will be maximization. Okay, but what is the statement that we're going to make? So here's what weak duality is saying. It says the following. Suppose that x bar and y bar are a primal dual pair of feasible solutions. So that is, x bar is a feasible solution for the primal and y bar is a feasible solution for the dual. Then we can say two things about these solutions. First of all, C transpose x bar is at most B transpose y bar. So this is something that we've already seen. This is because the dual, by construction, is meant so that B transpose y is an upper bound on C transpose x for any particular solution. So when you take any feasible solutions and you plug them into their objective functions, the value that you get for the primal objective function when you plug x bar in is going to be less than the value that you get when you plug y bar in for the dual objective function. So that's by the construction of what the dual is. We have this bound here. The second statement follows directly from the first. So the second statement is saying that if C transpose x bar actually so happens to equal B transpose y bar, then that must mean that x bar and y bar are optimal solutions for the primal and dual respectively. So we know that C transpose x bar is at most B transpose y bar. That's what the first thing is saying. And then that implies the second thing, actually, because if B transpose y bar is an upper bound on C transpose x, then if C transpose x bar actually attains that upper bound of B transpose y bar, then we couldn't have done any better than that. So that, but we've actually attained that upper bound. So x bar must have been an optimal solution. And similarly, B transpose y bar could not be anything below C transpose x bar. So if it actually so happens that B transpose y bar goes all the way down to this value of C transpose x bar, well, it couldn't have gone any lower. So that must mean that y bar is an optimal solution for the dual, because in that case we're trying to minimize. So that is a consequence of the first statement. And so again, we're not saying that this will happen. We're saying that if it so happens that C transpose x bar equals B transpose y bar, that is when we can conclude that that's a pair of optimal solutions, x bar and y bar. Okay, so let's see how this first works in the context of an example. So here is an example linear program that we will look at for this video. And it's a maximization problem for our primal here. And so we'll take the dual of it, and then we will look at a primal dual pair of feasible solutions and see what weak duality can tell us about that primal dual pair of feasible solutions. So first of all, we need to take the dual of this. But if you'll notice, it is a maximization problem, but we're not really sure as it stands how to take the dual of this, because it's not of the appropriate form. It's not in any of the forms that we're used to. There's not any uniform constraints on it. You see we have some greater than or equal to constraints, less than or equal to constraints, all sort of mixture there. And then same thing with the variables. They're not, some of them are free, some of them are non-negative, and so it's just kind of a mix of all sorts of constraints. So it's not really clear how to take the dual of this right away. So what we're going to do is we're going to convert it into this most general form up here. So maximizing the objective function subject to the constraints will be rewritten as all matrix less than or equal to constraints, and then the variables will all be free. So right now we have not all less than or equal to constraints, and the variables are not all free. So let's account for that first, then we can take the dual. Okay, well, first of all, we're not going to change the objective functions. We're still going to be maximizing 12, 26, 20 times x. So those are the coefficients. So just to be clear that x is the vector, x1, x2, x3. And so this is the linear combination of 12x1 plus 26x2 plus 20x3, as you would guess. That's effectively dot product. Now the constraints are such that, so first of all, do you see this top constraint here? So this one that I'm circling right now, that is a greater than or equal to constraint. And the way that you change a greater than or equal to constraint into a less than or equal to constraint, which is what we want all of our constraints to become, is we just divide by -1 on both sides. So let me just draw a matrix here for our constraints, and we're going to divide by -1, so we'll have -1, -2, -1 times x is less than or equal to -2. I'm sorry, not to -2, now to +2, because we divided by -1. So this is an equivalent constraint to the above. It's the same constraint, the same x's that satisfy the above constraint satisfy this. And now the constraint is of less than or equal to type. Okay, so the next constraint, so let me erase that up top there. The next constraint is 465 times x is less than or equal to 2. So that was already less than or equal to, so we can keep it as is. So 465 times x is less than or equal to 2. And then we have 2 minus 1 minus 3 is equal, times x is equal to 13. So for an equals to constraint, you have to replace it with a greater than or equal to and a less than or equal to simultaneously. That's the same thing as being equal to if it's both greater than or equal to and less than or equal to. So, and then with that greater than or equal to constraint, you again change it to a less than or equal to by dividing by -1. So let's first write the less than or equal to constraint. So we'll have 2 minus 1 minus 3 times x is less than or equal to 13. And then there's going to be another constraint that we now need to add. So let me make this matrix a bit longer, like that. And we'll divide by -1 on both sides. Well, -2, +1, +3 is less than, or times x is less than or equal to minus 13. So these two constraints that we've just written down are equivalent to the original single equality constraint. Okay, and so that accounts for all the matrix constraints. Now we have to deal with these variable constraints. You see, what we want is for all the variables to be free variables, but right now we have variable non-negativity enforced for x1 and x3. So what we do is, you see that we want those constraints to still be imposed, but we are not going to explicitly impose those constraints anymore. We are going to implicitly be imposing those constraints by encoding them into the matrix. That is, the matrix is going to absorb these constraints into it, so that outside of the matrix we can claim that the variables are free. So let me show you what I mean. So x1 being non-negative, we can encode that as a matrix constraint because a less than or equal to constraint, specifically we divide by both sides by -1, and we'll have minus x1 is less than or equal to 0, and that is a constraint that we can write inside the matrix. So we're going to add more constraints on to this matrix now. So we'll have -1, 0, 0 times x is less than or equal to 0. And you can see that this constraint that we've just written down, there's zeros for the second and third coefficients. So this is picking out exactly x1, and it's minus x1 is smaller than 0, or in other words, positive x1 is greater than or equal to 0, which is exactly the non-negativity constraint that we wanted to impose. But we no longer need to explicitly impose it as a variable constraint. Instead, it is now implicitly imposed as a matrix constraint. And then finally, the same thing has to happen. So we'll have 0, 0, minus 1 times x is less than or equal to 0. That accounts for x3 being non-negative. So this is all of the constraints, and now we can write that x1, x2, and x3 are all free, or in other words, the vector x is free. And so we know very well that, in fact, x1 and x3 will have to be non-negative because we've imposed these last two constraints here, but that's just what we secretly know because we implicitly impose those constraints by adding them to the matrix. it's just the x's have to satisfy whatever constraints appear in this matrix here. In particular, they will have to satisfy these last two, which makes them both non-negative. But at least now we don't have to explicitly write them as variable constraints, so that we can explicitly say that the variables are free. And now we know how to take the dual, because this format is familiar to us. So let me just draw some parentheses on the right-hand side, because this is a vector on the right-hand side after all. And now we have all less than or equal to constraints and free variables. Okay, so here it is cleaned up. So it's the same thing up top here. Right here is the primal and same coefficients, 12, 26, 20. And you can see these extra constraints added on down here for the non-negativity of x1 and x3. And then here is the dual below. So the coefficients 12, 26, 20, they became the right-hand side components, and vice versa for the right-hand side components to coefficients. The matrix becomes transposed. Less than or equal to constraints in the primal correspond to variable non-negativity constraints in the dual, and all the variables being free in the primal corresponds to equality constraints in the dual. Okay, and so now what we're going to do, now that we have our primal-dual pair of linear programs, I'm going to essentially pull out of thin air a primal-dual pair of feasible solutions. So you're not going to really know where these are coming from. We'll probably get into how we can find such solutions later on, but for now I'm just going to give these solutions to you so we can illustrate the weak duality principle. So here are the solutions. So x bar is going to be a feasible solution for the primal, and it'll be 5, -3, 0. And y bar is going to be a feasible solution for the dual, and it'll be 0, 4, 0, 2, 0, 0. And so if you take a moment, you can verify that these are in fact feasible solutions to the primal and dual. I won't go through all the fact that it satisfies all the constraints, but let me just go through one constraint each. So for instance, for this top constraint, we will have 5 times -1, which is -5, plus -3 times -2, which is +6. So we have -5 plus 6, and then the 0 times the -1 goes away. That's just 0. So we have -5 plus 6 is 1, and that is less than 2. So we've satisfied the first constraint, and similarly, this will satisfy all of the constraints. You see, for instance, 5 and 0 are the x1 and x3 components, and they're non-negative, which satisfies these bottom two constraints, for instance, and etc. So it satisfies them all. And y bar, similarly, we can verify it satisfies a constraint. So this one's actually a bit simpler because we have all zeros for all the components except for the second and fourth components. So we only need to care about the second and fourth components, which are 4 and 2 respectively. So we have 4 times 4 plus 2 times -2, and that's 16 minus 4 is 12, and that's exactly equal to the right-hand side. So you can see that it satisfies the first constraint, and similarly it satisfies all three of those equality constraints, and it's also a non-negative vector. So this really is a primal dual pair of feasible solutions, and what we're going to check now is what happens when we plug these into the objective functions, their respective objective functions at least. So we have C transpose X bar, and first of all, well, let's just compute it. So this is going to equal, so we're going to have 5 times 12, that's 60, which I'll write here, and then -3 times 26 is -78. And then the 0 times the last part goes away, so we're left with 60 minus 78, and that equals -18. So that's what happens when you plug in x bar into the primal objective function. And so what weak duality is telling us, in part, is that no matter what happens when we plug in y bar to its objective function, we get that we get that it will be larger, at least as large as -18. There's no way when we plug in y bar to this objective function down below that we're going to get anything less than -18. So this is less than or equal to B transpose Y bar, and this equals, again, we only need to worry about the second and fourth components. So we have 4 times 2, which is 8 minus 2 times 13, so minus 26. And so that is actually also minus 18. So you see that we got the same thing for both objective functions. So what we just found actually, so we can say therefore, that's the triple dots, we have that C transpose X bar equals B transpose Y bar. And again, what weak duality tells us now is that since there was no way that C transpose X bar was going to be anything more than B transpose Y bar, and vice versa for B transpose Y bar being less than C transpose X bar, the fact that they're actually equal to each other means that both X bar and Y bar must have been optimal solutions for their respective linear programs. So without really doing a tremendous amount of work, other than the fact that we were just given these vectors for free, once we do have the vectors, we can verify that they satisfied some condition which implies that they really are optimal solutions. So an optimal solution to the primal linear program is this X bar here, and it provides an optimal output of minus 18. You're not going to find anything larger than minus 18 for this linear program. And similarly, Y bar gives an optimal value of minus 18 for the dual, so you're not going to find anything less than minus 18 for the dual. So one more time, I'll say therefore, X bar is optimal for the primal, and Y bar is optimal for the dual. Okay, and in this way, by weak duality, we have just found a primal dual pair of optimal solutions for the primal and dual. So let's think about what the logical consequences of this are in more generality now. So what this is really going to be telling us, the weak duality that is that the feasibility of primal and dual pairs of linear programs are not going to be independent. That is, you cannot have, you see this chart here, this is all the possible outcomes for the primal and the dual. Any linear program is either going to have an optimal solution, or it's going to be unbounded, or it's going to be infeasible. Those are the only 3 things that can happen for any linear program ever. And so here's all the pairs of outcomes that can potentially happen when you're considering a primal dual pair. Here's the outcomes for the primal, and here's the outcomes for the dual, and this 3 by 3 grid of 9 cells here gives all the primal dual pair outcomes. And they are not all possible. That is, sometimes if you know something about the feasibility of the primal, or maybe lack thereof, that will in turn tell you something about the feasibility of the dual. They do not come independently from each other. So let's fill in this chart, because we can actually make a lot of progress on what possible outcomes, what outcomes are possible and what are not. So I'm saying possible outcomes of primal dual pairs. Let me just underline the word possible here. So possible means, we're not saying it will happen every time when you take a primal dual pair, we're just saying that it is a potential outcome. So, for instance, if the primal has an optimal solution, is it possible that the dual linear program also has an optimal solution? And the answer to that is yes, because actually we just saw an example of that in action. So I will fill in that cell with a green check mark. Let me make that a bit more of a check mark. Okay. Yeah, this is what just happened in this example that we just did. We found a primal dual pair of linear programs which both had an optimal solution. So this outcome is a possible thing that can happen. In that example, in fact, we found that that the objective function values actually were equal to each other. That's not something that we're saying here. That was just an extra thing that happened in this case. We'll discuss when that happens in the future, but for now we're just saying, do they both have an optimal solution, independent of whether or not those solutions are equal to each other. But yes, it is possible that they can both have an optimal solution. Okay, and so what if the primal is optimal and the dual is unbounded? Well, there's lots of possibilities here. So let me just draw something down below here. So imagine the real axis. So this is the real numbers, and what you're supposed to do is imagine when we plug in um, a value for our objective function for the primal and for the dual. So let's imagine that the primal is maximization, like we've been doing, and the dual is minimization. So the primal will be smaller than the dual. So what we'll have is we'll have some value. I'm just going to use some notation here. I'll just say p. All right. How about this? I'll say opt p. So that's the optimal value of the primal, and we know that that has to be less than the, at most the optimal value of the dual. Okay, so here it is on the real number line. So these are numbers which are indicating optimal solutions. So let's consider the case when the primal has an optimal solution and the dual is unbounded. What would that mean for this picture down below? Well, what it would mean, since the dual is a minimization problem and we're trying to make it as small as possible, this value of opt d, if it's unbounded, that means we can push it all the way to negative infinity, which is going to the left. And so that in turn means that there's no values that are feasible for the primal, because if there were, then that would give us a lower bound on the dual, but there are no lower bounds since it's unbounded. So actually, the primal cannot be optimal while the dual is unbounded. So this is an impossible situation. So weak duality, the thing that says that the primal objective is smaller than the dual objective, that implies that this cannot happen. Okay, if the primal is optimal, can the dual be infeasible? So that one, we don't have enough information to conclude one way or the other about that. We haven't seen an example of it, nor can we really eliminate that possibility. So let me just put a blue question mark there, because we just simply cannot say whether that's a possible thing that can happen. Okay, if the primal is unbounded, can the dual have an optimal solution? Well, now, this is quite similar to what we just said, but now we're going in the opposite direction. So if the primal is unbounded, we're trying to increase as large as we possibly can, starting from the optimal value of the primal, and we're going as far to the right. We're going unbounded to the right. We're going off to positive infinity. So there can't be any solutions for the dual, because if there were, that would give us an upper bound on the primal, but there are no upper bounds on the primal. It's unbounded. So for entirely analogous reasoning as for what we did in this 1-2 cell, this 2-1 cell will also be impossible. Okay, so we have an impossible situation there as well. And similarly, if the primal is unbounded, the dual can't be unbounded, because in particular that would mean the dual is feasible, and so the dual cannot be feasible. So it's impossible. So that actually only leaves us with one thing that can happen. That is, if the primal is unbounded, that must mean that the dual is infeasible, because one of these three things has to happen for the dual, and the first two can't happen, so it must have been infeasible then, and that would make sense, because if there were any feasible solutions for the dual, then we would have an upper bound, but this is unbounded, so that can't happen. So we're only left with this option, and so this is not only is it possible, it's absolutely necessary when the primal is unbounded. It's necessary that the dual is infeasible. And finally, if the primal is the one that's infeasible, what about the dual? Well, if the primal is infeasible, can the dual be optimal? Well, this is kind of the same situation as above, where the primal is optimal. Can the dual be infeasible? We simply do not know enough to make a conclusion about that yet. So we'll have a blue question mark there as well. If the primal is infeasible, can the dual be unbounded? At first glance, I was thinking that no, that we don't. I'm sorry, we don't know enough information yet. But in fact, if you think for just a moment, we know that primal and dual come in pairs, and the dual of the dual is the primal. So actually, for the same reason that if the primal is unbounded and the dual is infeasible, that's a possible outcome. It's the same reasoning for this. So this is also necessary. necessarily true. Consider it from the dual's perspective. If the dual is unbounded, what happens to the primal is we're looking down a column here, and so if the dual is unbounded, the primal can't be optimal and it can't be unbounded because the dual is getting as low as it possibly can, and it goes all the way to minus infinity, so there can't be any feasible solutions for the primal. So the primal had to be infeasible then, and so for the same reason as for this cell, which is the 2-3 cell, this 3-2 cell is also possible, in fact necessary. And okay, and then finally, the last one, if the primal's infeasible, is the dual infeasible? We just do not know enough information yet. So weak duality has just informed us what the possible outcomes of this primal dual pair of feasibility outcomes can be. And we will be able to conclude more information in the future about duality in order to fill in the rest of this chart and to say even more about duality overall. Okay, so this came from weak duality, and we will have lots more to say about it in the future. That's it though for this video. Although one thing I will mention before we conclude is that through this filling out of the chart, we assume the primal was maximization and the dual was minimization, but nothing changes if instead we had said the primal was minimization and the dual was maximization. Again, the dual of the dual is the primal, so which one you consider maximization and which one you consider minimization doesn't matter. This is all symmetric. So just one being maximization dual and one being minimization, which you call which is kind of you just need to adopt a convention for any given moment that you want to have a concrete situation to deal with. But okay, so we did that, and now we filled the chart out. So that's it for this video. Thanks for watching.